Welcome to this lecture providing an introduction to expert systems. During this lecture, we'll start by defining expert systems, then we'll discuss why expert systems are useful to develop and utilize, then we'll examine the major components of expert systems, followed by distinguishing them from cognitive computers. Then we'll discuss the advantages and disadvantages of expert systems, and lastly, we'll discuss expert system shells. Let's begin by defining what expert systems are. The term expert system overlaps with a number of other names relating to the same or similar artificial intelligence strategy. These include knowledge-based systems, a knowledge-based decision support system, intelligent decision support systems, rule-based systems, and production systems. Let's review some different definitions of expert systems that have been provided over the years. First, Feigenbaum defined them as a computer system that emulates or acts in all respects with the decision-making capabilities of a human expert, typically in a limited domain. Goodall defined them as a computer system that operates by applying an inference mechanism to a body of specialist expertise represented in the form of knowledge. Lauritsen and Spiegelhalter defined them as a program intended to make reasonable judgments or give assistance in a complex area in which human skills are fallible or scarce. Cooper defined them as a program designed to solve problems at a level comparable to that of a human expert in a given domain. And Causey defined them as a system embodying specialist expertise, for example, medical knowledge. This diagram is meant to illustrate where expert systems lie with respect to artificial intelligence research as a whole. Here we can see expert systems as a subset of all knowledge-based systems, which is further a subset of artificial intelligence programs. The thing that distinguishes knowledge-based systems from artificial intelligence programs is that knowledge-based systems make domain knowledge an explicit, separate resource from the rest of the system. For example, separated from the algorithm components responsible for applying reasoning. And you might hear the terms expert systems and knowledge-based systems used largely interchangeably. However, the distinction is that expert systems focus on applying expert knowledge to difficult real-world problems. Recall from our lecture on the history of artificial intelligence that in the late 60s and early 70s, we saw the dawn of expert systems, which further accelerated into the 1980s. The earliest systems had a distinct focus on scientific problems, including organic chemistry and diagnosis within medical fields. At the time, and still indirectly true today, AI relies on human experts and human input. Specifically, we can think of experts as subject matter experts, including clinicians, researchers, lawyers, machinists, insurance adjusters, etc. Of note, experts do not have to be, and largely in general are not, experienced in computer science, artificial intelligence, or machine learning. Therefore, to develop expert AI systems, a collaboration is needed between domain experts and AI developers. In order to make an expert system, there are generally a few essential ingredients, the first of which is having content that is annotated and knowledge specified by experts in the target domain of application. Further, this knowledge must be organized and formally represented in a knowledge base, using an appropriate knowledge representation. Additionally, we'll need to select or develop an inference engine that will be responsible for reasoning with that knowledge. And lastly, we'll need some sort of user interface so that non-computer scientists can utilize the expert system software. Now, at a high level, let's look at some of the general characteristics of expert systems. First and foremost, they often utilize symbolic reasoning. In other words, knowledge must be represented symbolically through things like trees, rules, frames, or description logics. Expert systems also apply heuristics to guide the reasoning in an attempt to reduce the search space needed to find a solution with reasoning. Reasoning can also be deductive when working with certainty, or it can be inductive when working with uncertainty. Search is an essential aspect underlying how these systems operate, with the goal of finding good or best solutions. We'll cover search and related strategies in separate lectures. Let's also take a look at some general capabilities of an expert system. For one, they're often regarded as uniquely good at explaining concepts in its reasoning process. In this way, it can behave similar to humans who can generally explain the things they're doing as they're doing them. Expert systems can also be used to give advice on various topics or options. It can be helpful in decision making, in other words, deciding between multiple options, or it can be used to give predictions or forecasts on future instances. And further, it can be used to generate accurate and relevant output for problems given an adequate knowledge base. In terms of their applications, there are many broad classes of expert systems. For example, they've been designed to handle configuration problems, aimed at assembling proper components of a system in the proper way. Or diagnosis, to infer underlying problems based on the observed evidence. Or instruction, providing intelligent teaching so students can ask why, how, or what if questions, just as if a human being were teaching. This application is largely thanks to expert systems typically having an explanation or justification component. Another area of application includes interpretation problems, where we want to explain observed data. Also monitoring, where we want to compare observed data to some expected data and judge performance. Or planning, where we want to devise actions to yield some desired outcome. Prognosis, where we want to predict the outcome of a situation. Remedy, to prescribe treatments for a problem. And finally, control, where we might want to regulate a process. Of note, a control system might also require interpretation, diagnosis, monitoring, planning, prognosis, and remedies, all achieved by one single system. Here are some examples of specific areas where expert systems have been used. In medicine, we have disease diagnosis, medical alert systems, and healthcare management. In finance, we have credit analysis systems, pension fund advisors, automated help desks, market surveillance systems, and business process re-engineering systems. In manufacturing, we have machine fault diagnosis, robotics, computer configuration, and materials spillage identification. And beyond that, they've been used in human resources, data processing, and homeland security systems. Now let's move on to discussing why expert systems are useful to develop and utilize. Putting together an expert system isn't a trivial affair. So why do people take the time to develop or use them? Well, first off, when it comes to human expertise, it's often in short supply, where there might only be a few experts in the world to begin with, or only a few available to work on the given task. Such experts can be expensive to develop or to hire, or they could simply be hard to get a hold of in a hurry. Also, sometimes even an expert has trouble applying their knowledge quickly, especially in very complex and high-pressure tasks. Further, it can be impractical financially to have a human constantly on call to be able to provide their expertise. Beyond this, experts can be lost due to retirement, leaving their job, or even death. Implicitly, expert systems serve the following functions with respect to expertise. When they're developed, they can serve to document or preserve expertise, to reproduce or make available that expertise on demand, and they can be used to teach or disseminate expertise that's been stored as part of that expert system. Beyond all of this, at the end of the day, computers don't get bored, tired, frustrated, or scared. So having distilled human expertise into a computational form can avoid some of those issues as well. Now let's think about expert system characteristics in contrast with other artificial intelligence systems. First, expert systems tend to deal with subjects of considerable complexity. Typically, they're focused in a narrow, specialized domain, and they provide expert-level solutions to complex problems. As mentioned before, the knowledge in expert systems is separated from its processing. This gives us a reusable shell framework for these systems that can make it easier to plug and play an expert system framework and adapt it to solve entirely new problems. Another thing that's emphasized in expert systems is the need to have high-quality performance. At the end of the day, the speed of a system doesn't really matter much if you get a wrong answer. However, with that in mind, it's still important that our expert systems be as fast as possible. In other words, a correct answer doesn't mean much if it comes too late. This could happen, for example, if a patient died while waiting for a treatment action, or if a nuclear power plant melted down because the expert system's safety controller failed to make a timely decision. We also want expert systems to be capable of explaining and justifying the solutions they come up with. This is just another way of saying that we care about their interpretability or their understandability. And lastly, we want them to be flexible. Often, expert systems are focused on domains where new information might be needed to be incorporated, or old information might need to be fixed, corrected, or updated. Now we'll move on to an overview of expert system components. Here is a high-level schematic of an expert system, where everything inside this dotted line is part of the expert system itself. On the left, we have a non-expert user who can query the system and get advice back. And inside the expert system, we generally have a user interface, an inference engine, and the all-important knowledge base that has been assembled based on the knowledge from expert human beings in the real world. Ultimately, the purpose of an expert system is to replace, by automation, or provide support for human experts in solving or advising on real-world problems. There are two essential components of an expert system. The first being the knowledge base. This is the home of symbolically and formally represented knowledge that can take on many representations that we've mentioned. The second key component is the inference engine. This is responsible for reasoning, in other words, drawing conclusions from the knowledge base. Critically, the reasoning or inference approach must pair with the representation being used. So if you have an expert system that was designed to work with rules, you couldn't simply replace them with trees or frames without expecting some major issues that might need to be resolved, or indeed thinking about completely redesigning the expert system from scratch. In addition to those essential components, there are also some other common components of an expert system. For one, we have a user interface. This is just a mechanism by which the user and the system can communicate with one another. Another possible component of an expert system is a knowledge base editor. This is also known as a knowledge acquisition facility. This basically provides an automatic way for the user to enter knowledge into the system, bypassing the need for explicit coding expertise. This can make it easier for non-computer science experts to help maintain, improve, and update an expert system. And lastly, expert systems often have an explanation system. This is also known as a justifier. This component is responsible for explaining the reasoning of an expert system to a user in the form of some natural language or something as close to natural language as possible. Here we have an expert system schematic, aiming to capture all of the different aspects of a typical expert system. Again, on the left, we have a user who can ask queries and get back advice. The user will generally interact via the user interface in yellow. This user interface is importantly connected to the inference engine, as well as generally to the knowledge base editor, the explanation system, and to parts of the knowledge base itself. In particular, the questions, which need to be asked to the user, and any case-specific facts that need to be directly entered by the user. The top green box represents the knowledge base editor that can transform user input into new rules, facts, and questions that can be formatted and inserted into the knowledge base. The orange box is the inference engine, responsible for reasoning, and which is directly connected to the knowledge base. The bottom green box represents the explanation system, which is connected to the case-specific facts currently in the knowledge base. We can also see the shell of an expert system being identified with the dashed line box. The shell represents the reusable part of an expert system framework, including the user interface, the knowledge base editor, the inference engine, and the explanation system. The shell is reusable because it can be paired with or used to develop any new knowledge base for some new application. And on the far right, in purple, we have the knowledge base, comprised of rules, general facts, questions, and case-specific facts. This table aims to outline some of the major differences between conventional computer programs and expert systems. For example, when it comes to control and data, conventional programming implicitly integrates the two, while expert systems explicitly separate them, as you've just seen. Also, in conventional programming, a solution is usually reached using an algorithm, while in an expert system, this comes from inference applied to rules. Also, when it comes to explanation, conventional programs usually don't have a mechanism to do this, but in expert systems, this is usually an important aspect. And lastly, looking at modifiability, conventional programs are usually difficult to modify, while expert systems usually offer a more reasonable and easier path to do so. Now let's take a moment to define and distinguish cognitive computers from expert systems. Cognitive computers are defined as a technology platform that aims to simulate human thought processes in a computerized model. They've also been referred to as cognitive computing systems, or cognitive systems for short. Cognitive computers use a combination of knowledge representation, inference engine, user interfaces, and potentially natural language processing, machine learning, and/or data analysis to mimic how the human brain senses, reasons, and learns. They're also generally designed to assist human decision-making, but not to replace it. In general, cognitive computers are made with algorithms. They're knowledgeable only about what is taught or learned, and they control only what is given to them to control. Cognitive computers generally can do very boring work for you, often make better, more consistent objective decisions than humans, and perform tasks faster without tiring. Recall the example of IBM Watson from our lecture on artificial intelligence history. This was considered to be an example of a cognitive computer. However, expert systems and cognitive computers aren't necessarily the same thing. While they share roots in artificial intelligence and cognitive science, including the study of human thought and linguistics, and they both simulate intelligence by creating a computer system that mimics human intelligence, however, they approach this in different ways. Expert systems focus on emulating human expert decisions in narrow specific fields like medical diagnosis or chemical analysis, and they tend to use a knowledge base of facts and if-then rules processed by an inference engine. And their nature is often rigid, relying on pre-programmed knowledge rather than deep learning or self-understanding. On the other hand, cognitive computers focus on simulating broader human cognition, including learning, reasoning, and understanding, in order to handle ambiguous problems. They tend to combine AI, machine learning, and human-computer interaction to process vast data, identify patterns, and understand natural language. Their nature aims for more adaptive, human-like interactions and incorporating complex tasks like speech recognition and narrative generation. Now we move on to the advantages and disadvantages of expert systems. To summarize the advantages of expert systems, they are likely best known for their natural knowledge representation, which uses human-readable if-then rules to provide a uniform structure that is self-documenting and where each rule is an independent, clear piece of knowledge. Expert systems can also deal with both incomplete and uncertain knowledge. They can be developed and updated in phases. They can facilitate knowledge transfer to remote geographic locations. They can provide consistent answers for repetitive decisions, processes, and tasks. They can combine multiple human expert intelligences, and they allow the centralization of decision-making processes. With regard to disadvantages, it's possible that expert systems may not arrive at a conclusion or even know if a conclusion is possible in some situations. Also, typically they work only well within a narrow domain of knowledge. Also, they're typically unable to learn or be creative, and this is because most knowledge bases typically avoid self-modification or improvement, as this can be risky and introduce errors. Also, rule search can be time-consuming and slow, and thus occasionally expert systems may be unsuitable for real-time applications demanding extremely fast decision-making. Also, the relationship between rules can be opaque. In other words, while individual rules are clearly interpretable, logical interactions among a large rule base may be difficult to understand, since the rules lack a hierarchical structure. As such, it can be difficult to understand how individual rules serve the overall strategy of the knowledge base. Also, typically, expert systems that are built on human past experiences, gut feelings, intuitions, or incorporate trial and error approaches can make incorrect suggestions to the user. Furthermore, expert systems cannot reason about related or new situations that have not been covered by the rule base explicitly. The process of knowledge acquisition to build an expert system can also be a major bottleneck to implementation. And like any AI system, there can be some potential for limited human trust, where users do not want to leave critical decisions to machines. Also, expert systems do not have access to common sense knowledge, so everything must be explicitly programmed into the system. They also can have a lack of flexibility and ability to adapt to changing environments. And lastly, expert systems are not suitable for all types of domains and tasks. For example, they're not useful or preferable in the following situations. For example, when efficient conventional algorithms are already known for a given task, when the main challenge is computation rather than knowledge, and when knowledge cannot be captured efficiently or used effectively in reasoning. Lastly, in this lecture, we'll cover expert system shells. As mentioned before, an expert system shell is the reusable, recyclable part of an expert system. We could think of the shell as being an expert system development tool, framework, or environment. It allows a developer to build an expert system by only generating a knowledge base. A shell simplifies the process of creating an expert system in a faster, cheaper, and more efficient way. However, the user must rely on a knowledge representation that the shell's inference engine can reason with, which are typically rules. Of note, different shells may include different components, use different terminology, a different coding language, and different syntax for implementing rules, facts, etc. Going back to this schematic, we highlight the shell of an expert system once more as being this dotted green line surrounding some of the major components of the system. Looking at some shell characteristics, good shells typically also provide facilities for communication with external sources, including database management systems, spreadsheets, and graphics packages. Some other non-essential but extremely useful features include the ability to handle both forward and backwards chaining for reasoning, handling certainty and uncertainty to perform deductive and inductive reasoning, and including a knowledge base editor, a user interface, and an explanation system as standard secondary components. Here we give a listing of some example expert system shells that have been proposed over the years. One of the best known classic shells is called CLIPS, standing for C Language Integrated Production System. CLIPS was developed by NASA in the 1980s, and is still largely one of the most famous and widely used expert system tools today. It has been described as highly portable and low latency, focusing on forward chaining reasoning. It can also be easily extended to handle uncertainty. CLIPS is free to download and use, and more information can be found through this web link. Another classic shell is called JES, standing for Java Expert System Shell. This was a clone of CLIPS written entirely in Java, and was designed for seamless integration with Java code and libraries, making it popular for web-based expert systems. JES supports both forward and backwards chaining, but not uncertainty. More information about JES can be found at this link. Now let's look at some Python expert shells. The first is Pike, which stands for Python Knowledge Engine. This shell was inspired by Prolog and is a knowledge-based engine that performs both forwards and backwards chaining, but does not handle uncertainty. It compiles rules in Python code for speed, and more information can be found at this web link. Another Python example is PyClips, which is a Python module that provides a bridge to the traditional Clips engine, allowing you to use Clips's power within a Python environment. More information can be found at this link. Yet another is ClipsPy, a Python module that brings Clips capabilities within the Python ecosystem. More information can be found at this link. And Experta, a Python library for building expert systems strongly influenced by Clips. It is designed to be a modern Pythonic implementation of the Clips logic. More information can be found at this link. Further, we'll point out a couple enterprise and industrial frameworks, including Drolls, described as a powerful open-source business rules management system written in Java. It uses the REAT algorithm and is widely used in enterprise environments for business logic. More information can be found at this link. Also, there's Open Clinical, described as a repository and set of tools specifically for building medical expert systems and maintaining clinical knowledge bases. More information can be found at this link. And lastly, we'll give a historical expert system shell as a reference example. Here we have eMycin, which is essentially the original Mycin expert system, but having removed its medical rules. To summarize this lecture, expert systems represent some of the most successful early strategies for real-world AI application. Expert systems can allow us to capture, preserve, and disseminate knowledge and automated expert decision-making. Expert systems excel in narrow, specialized domains. Critical components of an expert system include a knowledge base and an inference engine, but often become more useful when also including a user interface, knowledge base editor, and an explanation system. Expert systems could be thought of as a basic type of cognitive computer, and several shells have been developed to help build and apply expert systems. I'm Ryder Benowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.